Hey everybody, my name is Scott, and today we will be solving the trim a binary search tree problem on LeetCode. Let's go a little bit into what a binary search tree is, just in case anyone watching doesn't really know. Well, a binary tree is a tree where each node in the tree has a left and a right child. It has two children per node, why it's called a binary tree. What's special about a binary search tree is that it has the property where for each node, all the nodes in its left subtree are less than or equal to the node's value, and all the nodes in its right subtree are greater than or equal to that node's value. So binary search trees are very helpful when it comes to things like searching the tree for a number. Because if we start at the root and we have these numbers stored in a binary search tree, we can find the number in log of n time. Because each decision we make while we're searching the tree, we cut the space we're searching for through in half. That's opposed to if they're just stored in a regular array and we wanted to find a number, we'd have to scan the entire array. It'd be a big O of n operation because we'd have to look at every element to see if we could find it. In a binary search tree, if you were looking for a number, again, it would just take log of n time. We won't go into all the reasons why it's log of n time, but the gist of it is each decision you make, you cut your search space in half. You either go left or you go right. So let's talk about this problem. It's to trim a binary search tree where we're given a binary search tree and a low and high index, L and R, and we want to trim the tree so that all elements lie in the range L to R. So the problem definition's pretty simple, and these are fun problems. Tree problems in general are pretty fun because it forces you to think recursively. A lot of times you can do things iteratively in trees, but the recursive solutions are usually the ones that make the most sense. So look at these examples here. Here's the binary search tree. There's left and right. They want all elements to be in the range 1 to 2. So this is the return. A tree of just 1, 2. This 0 gets trimmed out. Second example, more complicated tree. Indices are 1 to 3. So 3 stays at the root, 4 gets trimmed out, 0 also gets trimmed out, and then it just becomes this tree 3, 2, 1. And again, with that property of binary search trees we were talking about, look at the structure here. 3, 2 is less than 3, so it's its left child. 1 is less than 2, also its left child. 1 and 2, both less than 3, both in its left subtree. Let's implement it. This is a fairly simple problem with a couple of base cases to the recursion to think about. Just whenever you're going about these tree problems, like I said, thinking recursively is usually going to be your best way to start off trying to form a solution. So if we're going to write a recursive solution, let's write a base case so our recursion will bottom out. So if the root is null, what will we do? Let's just return null. Simple as that. So that will bottom out our recursion. Now let's start thinking about the different cases that can happen when our root is not null. What happens if the value of the root is equal to our left index? So the root's value, whatever the number stored at the root, is equal to left. Well, when we consider the properties of a binary search tree, what that must mean is that everything in the left subtree of the root is outside of our range, because everything in the left subtree will be less than L, so it'll be out of our range. So if the root's value is equal to left, what will we do? Well, we need to trim away that left subtree. So we'll set the root's left equal to null. And then what will we do with the right? Think about it for a second, what we should do with the right here. We can't just set it equal to its current right. because there may be values in that right subtree that while since everything to the right is greater than L, they won't be less, they won't be in the lower part of our bound. That would break it, but they could be greater than. So we need to trim the right subtree as well. So we'll make a recursive call. We'll pass in the roots right, so we're making our way down the tree. And we'll just keep L and R the same. So we'll recursively solve it for the right, and we will return the root. And you can probably guess what's coming next. What happens when the root's value is equal to the right? Well, again, our binary search tree properties state that in that case, everything to the right, everything in the right subtree of the root is outside of our bounds. It's higher than our higher bound. So we will trim away the right subtree. We will set the left subtree equal to the recursive solution of the left subtree. And we'll return that root. Root. So we've handled those two cases. What happens when the root's value is greater than both the left and the right? Think about that for a second. The root's value is greater than our left bound, and it's also greater than our right bound. What that must mean is that the root and everything to the roots in the root's right subtree is higher than our highest bound. So it all has to be trimmed away. So root's value will be greater than L, and it's also greater than R. Again, that means the root and everything in its right subtree needs to be trimmed away. We'll just return the recursive solution of the left. Great. So we've handled that case. And you can probably guess what's coming here as well. What happens if it's less than left and right? Simple, right? It's just the reverse. Everything in the left subtree and the root must be trimmed away. So we'll return the recursive call of the right. Alright, so none of these things have happened. Root's not null, value is not equal to left, value is not equal to right. It's not greater than both of them, it's not less than both of them. What must that mean? Where does that leave us? That means that we have a tree with a root. Its value is somewhere in our bounds. It's in between left and right. So what that also means is the node with the left value is in our left subtree. The node with the right value is in our right subtree. So this is where we just think recursively, and the recursive solutions magically solve our problem. We need to trim both the left and the right. And we return that root. Alright, let's give our code a run, see if we have any syntax errors, unknown errors, see if I'm still connected to the internet. Doesn't look like we do. Let's see, our answer is correct, matches up here. So let's submit the solution. Very nice. We got an accepted solution. Just to recap real quick, solving tree problems, it's not always the case, but usually you're going to want to start thinking recursively. solve something recursively on the left, something recursively on the right, put your answer back together. It's kind of the usual pattern. And if you don't know the structure of binary search trees that I was talking about, super important. I'd say after hash tables, probably one of the most important data structures out there that we have. So definitely want to go out there and do some reading on how binary search trees are put together and how they help our time complexity in different algorithms. So thanks for watching, and I'll see you next time.